Hi, welcome back to my class in linear algebra. Today we will take up solution of system of linear equations by using inverse matrix. And this method of solving system of linear equations using inverse matrix applies only to a system of linear equations with equal number of equations and number of variables. For our first example, consider the following system of linear equations. We are given 2x plus 3y equals 1 and minus 5x plus 2y equals 7. This is a system of linear equation with equal number of equations and number of variables. We have two linear equations and two variables. So the method using inverse matrix applies to this system of linear equations. If you have three linear equations and only two variables, then this method using inverse matrix will not apply. Similarly, if you have two equations in three variables, then this method using inverse matrix to solve system of linear equations will also not apply. And the first step is to write this system of linear equation in matrix form. At the left hand side, we start with the matrix whose entries are the coefficients of the variables. In the first column of this matrix, we write the coefficients of the variable x, positive 2, negative 5. In the second column of this matrix, we write the coefficients of the variable y. We have positive 3 and positive 2. And we multiply this square matrix, 2 by 2 square matrix, by a column vector or a matrix with only one column. And the entries of this one column are the variables in the given system of linear equations. The variables are x and y, and we write them as the entries of the first column or the entries of this column vector. The right-hand side of this matrix equation is also a column vector whose entries are the constant terms of the equations, or the right-hand sides of the given system of linear equations 1 and 7. If you multiply the first row of this square matrix by this column vector, you will get 2 multiplied by x, 2x plus 3y is equal to 1, and you get the first equation in the system of linear equations. If you multiply the second row of this square matrix by the column vector and equate the result to 7, you will get the second equation of this system of linear equations. Minus 5 multiplied by x plus 2y is equal to 7. And we get the second equation of the system of linear equations. Now we get the inverse of this square matrix, the matrix of the coefficients of the variables in the given system of linear equations. And we denote this by, we can denote it by matrix A. We find the inverse of this matrix using adjoint. Using adjoint and determinant, the Inverse of matrix A denoted by A to the minus 1 is equal to the adjoint of matrix A multiplied by the scalar 1 over the determinant of A. And if the determinant of A is not 0, then you conclude that the inverse of matrix A does not exist, and you conclude that the system of linear equation cannot be solved by using inverse matrix. To get the adjoint of A, we find the matrix whose entries are the cofactors of the entries of matrix A. And we start with cofactor of 2. The cofactor of 2 is denoted by C11, the entry in the first row and first column of the matrix whose entries are the cofactors of A. And the cofactor of 2 denoted by C11 is defined as negative 1 raised to 1 plus 1, where the first one is the row number of 2, and the second one is the column number of 2. And we multiply this by the determinant that remains after deleting the first column and the first row. And we get determinant of 2 is 2. We simplify minus 1 raised to 1 plus 1, or minus 1 raised to 2 is positive 1 multiplied by 2 is 2. We find the cofactor of 3. 3 is the element in the first row and second column. So the cofactor of 3 is denoted by C12. And the cofactor of 3 denoted by C12 is equal to negative 1 raised to the row number of 3, 1, plus the column number of 3, 2. Multiplied by the determinant that remains after deleting the first row and the second column. And you get minus 5. Minus 1 raised to 1 plus 2 is minus 1 raised to 3, that's negative 1, multiplied by negative 5 is positive 5. Next, we get the cofactor of negative 5, denoted by C21, because negative 5 is in the second row and first column. So the cofactor of negative 5 is denoted by C sub 21. And C sub 21 is equal to negative 1 raised to 2 plus 1. Multiplied by the determinant that remains after deleting the second row and the first column. And you get 3. You have negative 1 raised to 2 plus 1 is negative 1 raised to 3 is negative 1 multiplied by positive 3, that's negative 3. And the cofactor of this element 2 is denoted by C sub 22, because 2 is in the second row and second column. And cofactor of 2 is denoted by C sub 22. C sub 22 is equal to negative 1 raised to 2 plus 2 multiplied by the determinant that remains after deleting the second row and the second column, and the element that remains is 2, its determinant is 2. We simplify negative 1 raised to 2 plus 2 is negative 1 raised to 4. That's positive 1 multiplied by 2 is 2. And the adjoint of matrix A is the transpose. The transpose of the matrix whose entries are the cofactors of the elements of A. And the cofactors of these elements of A are 2, 5, and negative 3, 2. Hence, the adjoint of A is the transpose of this matrix, and we get the transpose of this matrix by writing the row as a column. We write the first row as the first column, and we write the second row as second column. Now we need to get the determinant of A, because we have to multiply the adjoint of A by the reciprocal of determinant of A. For 2 by 2 matrix, the determinant is obtained by like cross multiplication. 2 multiplied by 2 minus minus 5 multiplied by 3 minus minus 5 multiplied by 3. Minus 5 multiplied by 3 is negative 15. Negative 15 multiplied by negative is positive 15. Plus positive 15. 2 by 2 is 4. And 4 plus 15 is 19. 19 is not equal to 0. Therefore, A has an inverse. Again, if you get a determinant of 0, you conclude that the matrix has no inverse. And the given system of linear equations cannot be solved by the method using inverse matrix. The inverse now of A denoted by A to the minus 1 is equal to the reciprocal of the determinant of A. Determinant of A is 19 and its reciprocal is 1 over 19. Multiplied by the adjoint of matrix A given by 2, negative 3, 5, 2. The operation here is scalar multiplication. We multiply this matrix by the scalar 1 over 19. And to perform the multiplication, we multiply each entry of this matrix by 1 over 19. We get 2 multiplied by 1 over 19 is 2 over 19. One over 19 multiplied by minus 3 is negative 3 over 19. 1 over 19 multiplied by 5 is 5 over 19. And finally, 1 over 19 multiplied by 2 is 2 over 19. After you get the inverse of the matrix, you may check if this is correct. Multiply the inverse of A by A and you should get the identity matrix. But that is optional. We assume We take that means the correct inverse of matrix A. And after you get the inverse of matrix A, you multiply both sides of this matrix equation by the inverse of A. So the left hand side, we multiply by the inverse of A. 2 over 19 we multiply by this square matrix whose entries are the coefficients of the variables x and y. 2, 3 minus 5, 2. Multiply by this column vector xy. And the right hand side, we also multiply this column vector by the inverse of A. And we write first the inverse of A. 2 over 19, 5 over 19. The right hand side of the equation is equal to the inverse of A multiplied by this column vector 1 over 7. And we perform the operation multiplication at the left hand side. This is the inverse of A multiplied by A, and the product should be the identity matrix I. We check 2 over 19 multiplied by 2 is 4 over 19. Plus negative 3 over 19 multiplied by negative 5 is 15 over 19 plus 4 over 19. That's 19 over 19 is 1. We multiply the first row by the second column. 2 over 19 multiplied by 3 is 6 over 19. Plus negative 3 over 19 multiplied by 2 is minus 6 over 19. So that 6 over 19 minus 6 over 19 is 0. Next, we multiply the second row by the first column. 5 over 19 multiplied by 2 is 10 over 19 minus 2 over 19 multiplied by negative 5 is minus 10 over 19. 10 over 19 minus 10 over 19 is 0. Multiply the second row by the second column. 5 over 19 multiplied by 3 is 15 over 19. Plus 2 over 19 multiplied by 2 is 4 over 19. 15 over 19 plus 4 over 19 is 19 over 19 or 1. And we multiply this matrix by the column vector x over y. Column vector with entries x, y. But if you multiply this, we multiply each row by the column vector. And we also perform the operation multiplication at the right hand side. We multiply the first row by the column vector. 2 over 19 multiplied by 1 is 2 over 19. Plus minus 3 over 19 multiplied by 7 is minus 21 over 19. Hence we get 2 over 19 minus 21 over 19. That's negative 19 over 19 or 1. Or negative 1. Again, 2 over 19 multiplied by 1 is 2 over 19 plus minus 21 over 19, that's negative 19 over 19 or negative 1. Now multiply the second row by the column vector. 5 over 19 multiplied by 1 is 5 over 19 plus 2 over 19 multiplied by 7 is 14 over 19 plus 5 over 19, that's 19 over 19 or 1. We simplify the left hand side. Multiply the first row by the column vector. 1 multiplied by x is x plus 0 multiplied by y is 0. You get x plus 0 or x. Now multiply the second row by the column vector. 0 multiplied by x is 0 plus 1 multiplied by y is y. We get 0 plus y equals y. And two matrices are equal if they have the same size or shape. These are both column vectors of size 2 by 1 with 2 rows and 1 column. And the second condition for two matrices to be equal is that the corresponding entries must be equal. Hence, if they are equal, x is equal to negative 1. And y is equal to 1. And these are the solution of the given system of linear equation. We check by substituting the values of x and y into each equation. 2 multiplied by negative 1 is negative 2. Plus 3 multiplied by 1 is 3. Minus 2 plus 3 is 1. In the second equation, we replace x with negative 1 and we replace y with positive 1. Minus 5 multiplied by negative 1 is positive 5. Plus 2 multiplied by 1 is 2. We get 5 plus 2 equals 7. Therefore, these values of x and y are correct and they are the solution of this system of linear equations in two variables solved by using inverse matrix. For our second example, consider the following system of linear equations. We have a plus b minus c equals positive 4. A minus b plus c equals negative 2. Minus a plus b plus c equals 0. In this system of linear equations, we have three linear equations, 1, 2, 3, and three variables, a, b, c. Therefore, the method for solving system of linear equations using inverse will apply. But only if the determinant whose entries are the coefficients of the variables a, b, c is not equal to 0. And the first step again, we write the system of linear equations in matrix form. At the left hand side, the first matrix is a square matrix whose entries are the coefficients of the variables in the given system of linear equations. This is a square matrix with entries in the first column equal to the coefficients of variable a. Coefficient of a in the first equation is 1. Second equation, coefficient of a is 1. In the third equation, coefficient of a is negative 1. Hence, the entries of the first column are 1, 1, negative 1. Entries of the second column are the coefficients of variable y in the given system of linear equations. We have positive 1, negative 1, and positive 1. And entries of the last column are the coefficients of the third variable c, negative 1, positive 1, positive 1. And we multiply this 3 by 3 matrix by a column vector whose entries are the variables in the given system of linear equations A, B, C. The right-hand side of the matrix equation is another column vector whose entries are the constant terms of the equations 4, -2, 0. And we find the inverse of this 3 by 3 matrix. We denote this by A. And using adjoint, the inverse of A, denoted by A to the -1 equals the adjoint of matrix A multiplied by the scalar 1 over the determinant of A. And we start by getting the determinant of A, so that if we get a 0 for determinant of A, we need not get the adjoint of A. If the determinant of A is equal to 0, we stop and we conclude that the inverse of A does not exist, and the given system of linear equations cannot be solved using inverse matrix. And for a 3 by 3 matrix, you can find its determinant in 6 ways in terms of any of the 3 rows or any of the 3 columns, but I will use the entries of the first row. The first entry in the first row is 1, and we multiply 1 by its cofactor. And the cofactor of -1, the cofactor of 1 is equal to -1 multiplied by the row number and column number of this entry 1, which are 1 and 1. Plus the determinant that remains after deleting the first row and the first column, you get -1, 1, 1, 1. The next entry in the first row is 1. We write +1. Multiplied by the cofactor of 1, given by -1 raised to the row number of this element 1 is 1, plus the column number of this element 1 is 2. -1 raised to 1 plus 2. Multiplied by a determinant that remains after deleting the first row and the second column. And you get 1, 1, -1, 1. The last entry in the first row is -1 plus -1. Multiplied by the cofactor of -1, given by -1 raised to row number plus the column number of -1, which are 1 and 3 respectively. Hence, -1 raised to 1 plus 3. Multiplied by the determinant that remains after deleting the first row and the third column. We have a 2 by 2 matrix with 2 by 2 determinant with entries 1, -1, -1, 1. And we simplify each term. We have negative 1 raised to 1 plus 1, that's 1. Negative 1 square is positive 1. Multiplied by 1 is positive 1. Multiplied by this determinant of order 2. 1 times negative 1 is negative 1. Minus 1 times 1 is minus 1. We have minus 1 is minus 2 multiplied by 1 minus 2. The second term, negative 1 raised to 1 plus 2 is negative 1 raised to 3. And negative 1 raised to 3 is negative 1. Multiplied by 1 is negative 1. Multiplied by this determinant of order 2. 1 times 1 is 1. Minus 1 times 1 is negative 1. We have 1 minus negative 1 is positive 1. We have 1 plus 1 is 2 multiplied by negative 1 minus 2. And the last term, negative 1 raised to 1 plus 3 is negative 1 raised to positive 4. That's positive 1 multiplied by negative 1 is negative 1. And 1 times 1 is 1 minus negative 1 times negative 1 is positive 1. So we have 1 minus 1 is 0. Multiplied by negative 1 is 0. And so the determinant of the last term is 0. Determinant of A is minus 2 equals negative 4. And the determinant of A, negative 4 is not equal to 0. Therefore, this matrix has an inverse, and we can solve this system of linear equations using inverse. We now find the inverse of A by getting first the adjoint of A. And the adjoint of A is the transpose of the matrix whose entries are the cofactors of the entries of matrix A. And we start with the cofactor of 1. Cofactor of 1 we denote by C11 because 1 belongs to the first row and first column. And this cofactor of 1 is equal to negative 1 raised to 1 plus 1. Multiplied by the determinant that remains after deleting the first row and the first column. We have minus 1, 1, 1, 1. And we simplify. Minus 1 raised to 1 plus 1 is minus 1 raised to 2. That's positive 1. Multiplied by minus 1. Minus 1. That's minus 2. Multiplied by positive 1 minus 2. And that's the first entry of the first row of the matrix whose entries are the cofactors of the elements of A. Cofactor of 1 is minus 2. Next, cofactor of this entry 1 denoted by C sub 1, 2. Because this entry belongs to row 1 and second column. Is given by minus 1 raised to 1 plus 2. Multiplied by a determinant that remains after deleting the first row and the second column. You get 1, 1, negative 1, 1. We simplify negative 1 raised to 1 plus 2 is negative 1 raised to 3. That's negative 1. Multiply by this determinant of order 2. We have 1 times 1 is 1 minus negative 1 times 1 is negative 1. That's 1 plus 1 is 2. Multiply by negative 1 is negative 2. Now we find the cofactor of negative 1. Cofactor of negative 1 is denoted by C13 because negative 1 belongs to the first row and third column. And this cofactor of negative 1, C13 is given by negative 1 raised to 1 plus 3. Multiply by determinant of order 2 obtained after deleting the first row and the last column. 1, negative 1, negative 1, 1. We simplify negative 1 raised to 1 plus 3. That's negative 1 raised to 4. And that's positive 1. Multiply by this determinant of order 2. 1 times 1 is 1. Minus negative 1 times negative 1 is 1. We get 1 minus 1 is 0. Multiply by positive 1 is 0. We are now in the second row. Cofactor of 1 denoted by C21. C sub 21, cofactor of 1 in the second row is equal to negative 1 raised to 2 plus 1. Multiply by determinant that remains after deleting the second row now and the first column. And you get 1, negative 1, 1, 1. We simplify negative 1 raised to 2 plus 1 is negative 1 raised to positive 3. That's negative 1. Multiply by this determinant of order 2. 1 times 1 is 1. Minus 1 times negative 1 is negative 1. We have 1 minus times negative 1. That's 1 plus 1 is 2. Multiply by negative 1 is negative 2. Now the cofactor of negative 1, this entry belongs to second row and second column. Hence cofactor of negative 1 is denoted by C sub 22. And the cofactor C sub 22 is given by negative 1 raised to 2 plus 2 multiplied by the determinant that remains after deleting the second row and the second column. And we get 1, negative 1, negative 1, 1. Again, we simplify. Negative 1 raised to 2 plus 2 is negative 1 raised to 4. That's 1. Multiply by this determinant of order 2. 1 times 1 is 1. Minus negative 1 times negative 1 is positive 1. You get 1 minus 1 is 0. Multiply by 1 is 0. Now we find the cofactor of this one in the second row and third column, and its cofactor is denoted by C sub 2, 3. The cofactor C sub 2, 3 is equal to negative 1 raised to 2 plus 3 times determinant that remains after deleting the second row and third column, and we get 1, 1, negative 1, 1. We simplify negative 1 raised to 2 plus 3, that's negative 1 raised to 5. And negative 1 raised to 5 is negative 1 multiplied by this determinant of order 2. 1 times 1 is 1. Minus negative 1 times 1 is negative 1. Therefore, we get 1 minus negative 1. That's 1 plus 1 is 2 multiplied by negative 1 is negative 2. We are now in the last row and third row. Cofactor of negative 1 is denoted by C sub 3, 1 because negative 1 belongs to the third row and the first column. And the cofactor C sub 3, 1 is given by negative 1 raised to 3 plus 1. Multiplied by determinant that remains after deleting the first row and the first column. We get 1, negative 1, negative 1, 1. We have negative 1 raised to 3 plus 1 is negative 1 raised to positive 4. Negative 1 raised to positive 4 is positive 1. Multiplied by this determinant of order 2, we have 1 times 1 is 1 minus negative 1 times negative 1 is positive 1, that's 1 minus 1 is 0. Multiplied by 1 is 0. And the cofactor of this entry 1 is denoted by C sub 3, 2. The cofactor C sub 3, 2 is given by negative 1 raised to 3 plus 2 times the determinant that remains after deleting the third row and the second column. This is 3, 2. Element in the third row and second column, we delete the last row. And the second column, we get 1, negative 1. 1, 1. We simplify negative 1 raised to 3 plus 2 is equal to negative 1 raised to 5, which is equal to negative 1 multiplied by this determinant of order 2. 1 times 1 is 1 minus 1 times negative 1 is negative 1. So we have 1 minus 1. That's 1 plus 1 is 2. Multiplied by negative 1 is negative 2. Finally, the cofactor of the last entry in the last row, 1, denoted by C sub 3, 3, is given by negative 1 raised to 3 plus 3. times the determinant that remains after deleting the last row, the third row and the third column. And we get 1, 1, 1, negative 1. And we simplify negative 1 raised to 3 plus 3, that's negative 1 raised to positive 6. Or positive 1 multiplied by this determinant, negative 1 minus 1 times 1 is 1. Minus 1 is negative 2. Multiplied by positive 1 is negative 2. And we have this matrix whose entries are the cofactors of the entries of matrix A. And we get the transpose of this matrix to get the joint of A by writing each row as column. The first row becomes the first column, negative 2, negative 2, 0. And the second row becomes the second column, negative, the second column now, entries are negative 2, 0, negative 2. And the last column entries are 0, negative 2, negative 2. And this matrix is the adjoint of A. And the adjoint of A we multiply by the reciprocal of the determinant of A, or reciprocal of minus 4. And the result is the inverse of matrix A. We now find the inverse of matrix A. We take the reciprocal of the determinant of A, and the determinant of A we found earlier is equal to negative 4. And its reciprocal is 1 over negative 4, or negative 1/4. We multiply the reciprocal of determinant of A, negative 1/4, by the adjoint of A, given by this matrix, negative 2, negative 2, 0. Negative 2, 0, negative 2. And the last row has entry 0, negative 2, negative 2. To perform the scalar multiplication, we multiply each entry of this matrix by negative 1/4. Negative 1/4 multiplied by negative 2 is positive 2 over 4. In lowest terms is 1/2. Negative 1/4 multiplied by negative 2, that's positive 2 over 4. In lowest terms is 1/2. Negative 1/4 multiplied by 0 is 0. Now we multiply each entry of the second row by negative 1/4. Negative 1/4 multiplied by negative 2, that's positive 2 over 4 in lowest terms is 1/2. Negative 1/4 multiplied by 0 is 0. Negative 1/4 multiplied by negative 2, that's positive 2 over 4, or 1/2. Negative 1/4 multiplied by 0 is 0. Negative 1/4 multiplied by negative 2, that's positive 2 over 4, in lowest terms is 1/2. Negative 1/4 multiplied by negative 2, that's positive 2 over 4 in lowest terms is 1/2. And this is the inverse of matrix A. We will now multiply both sides of this matrix equation by the inverse of A. We start from the left hand side, inverse of A multiplied by this column vector equals the inverse of A multiplied by this column vector. This is the inverse of A. We multiply this by A. 1, 1, negative 1. Multiply by the column vector ABC. Equals the inverse of A. Multiply by this column vector, whose entries are the constant terms of the equations. We perform the operation multiplication of the left hand side, and we should get the identity matrix because we have here the product of the inverse of matrix A and matrix A, and we should get the identity matrix. We have 1/2 multiplied by 1/2, that's 1, plus 0 is 1. We now multiply the first row by the second column. 1/2 minus 1/2 is 0, plus 0 is 0. The first row by the third column. Minus 1/2 plus 1/2 is 0, plus 0 is 0. We now multiply the second row by the first column. We have 1/2 plus 0 minus 1/2 is 0. Multiply the second row by the second column. 1/2 minus 0. 1/2 plus 0 plus 1/2 is 1. And minus 1/2 plus 0 plus 1/2 is 0. Now we multiply the last row by each column. We have 0 plus 1/2 minus 1/2 is 0. 0 minus 1/2 plus 1/2 is 0. Multiply now the last row by the third column. 0 plus 1/2 plus 1/2 is 1. We multiply by the column vector ABC. And we also perform the operation matrix multiplication at the right hand side. Multiply each row by the column vector. We have 1/2 multiplied by 4 is 2. 1/2 plus 1/2 multiplied by minus 2, that's minus 1. Plus 0 multiplied by 0 is 0. Therefore, we get 2 minus 1 plus 0 is 1. Now, multiply the second row by the column vector. We have 2 plus 0 plus 0 is 2. And multiply the last row by the column vector. We have 0 minus 1 plus 0 is minus 1. And this identity matrix multiplied by this column vector. And the identity matrix, because it's an identity element, if you multiply the identity matrix by a matrix, the result is the matrix. But we check, we multiply each row of this identity matrix by the column vector. We have 1 multiplied by A is A, plus 0 is A. Multiply the second row by the column vector. 0 multiplied by A is 0, plus 0 is B. And multiply the last row by the column vector. 0 plus C is C. And these two matrices are equal if they have the same size. That's the first condition. They are both 3 by 1 matrix, or they are both column vectors. And the corresponding entries must be equal. Therefore, A is equal to 1, B equals 2, and C equals negative 1. And these are the solution to the given system of linear equations. We check by substituting the values of A, B, C in each linear equation. A is 1, B is 2, that's 3. And C is negative 1 multiplied by negative 1, that's positive 1 plus 3 equals 4. We have 1 minus 2 is negative 1, and C is negative 1 minus 2. A is 1, B is 2, that's 1, and C is negative 1, 1 minus 1 is 0. Therefore, these are the correct solutions to the given system of linear equations that we solve using inverse matrix. For your practice in solving system of linear equations using inverse, please try the following problems. Solve by inverse matrix. Number 1, A minus B equals 1, minus A plus 2B equals 0. The first step is to check whether the given system of linear equations has equal number of equations and number of variables. If the number of equations and the number of variables in the given system of linear equations are equal, then you proceed to solving the given system of linear equations by matrix inverse. And before you get the inverse of matrix, you check first if the determinant of the matrix whose entries are the coefficients of the variables is not equal to 0. If the determinant of the matrix whose entries are the coefficients of the variables in the given system of linear equations is 0, you stop and you conclude that the inverse does not exist and the system cannot be solved by using matrix inverse. And that's the time that you will apply a different method. For number 2, u minus 3v equals negative 3, 2u plus b equals 8. In number 3, we have x minus y plus 2z equals 1. 2x plus y minus c equals negative 3. Minus x plus 2y plus c equals 0. And last, 3a minus 2b plus c equals 7. 2a plus b minus 3c equals negative 5. a minus 3b plus 2c equals 8. And that completes our lesson for today. In the next lesson, we will solve again system of linear equations using determinant.